Are you curious about the magic behind machine learning algorithms and their ability to solve complex problems? So today we'll delve into this fascinating world of ML and we'll explore the heart and soul of the field. Essentially algorithms like decision trees, sport vector machines, naive Bayes, k-nearest algorithm, clustering, random forest, gradient boosting, dimensionality reduction techniques and regression based techniques. So first start with the naive Bayes technique. So this naive Bayes is a simple and effective machine learning algorithm used for classification tasks. So imagine you are a detective who is trying to identify a thief based on its characteristics such as the height, eye, color and age. So how the naive Bayes algorithm will help you determine the likelihood of each suspect being the thief based on available evidence. So here the algorithm will work by calculating the probability that a particular suspect belong to a class A, that is the thief in this class, based on the set of features, say its height, eye, color and age. It will use this Bayes theorem which states that the probability of that event, that is P class, occurring given another event, that is P data, has occurred and can be calculated using P class by data, that is P data by class into P class by P data. So like this. So in naive Bayes, each class, that is thief, has a prior probability, that is P class, and a set of features probability, that is P data by class. And for example, the prior probability of the suspect being the thief, that is P class, is calculated based on the overall population of the thieves and the features probability. That is this one. Okay, so that will represent the likelihood of thief having a specific height, eye, color and age. Now this algorithm will calculate the probability of each suspect in class and will assign the suspect with the highest probability as the most likely thief. Why it is called naive? Because it assumes that features are conditionally independent, meaning that the presence of one feature does not affect the probability of other. That's why it's called naive. So in practice, this assumption may not be entirely accurate, but it simplifies the calculations and often yields a good results. So to summarize this, we can say that this naive Bayes algorithm is a probabilistic classifier that assigns a class to an instance based on the likelihood of these available features. So despite its simplifying assumption, it's powerful and efficient algorithm that works well in many applications. Now comes with the linear regression. So this linear regression is a statistical method used to model the relations between a dependent variable, that may also be called a response or an outcome variable, and one or more independent variable, that is the features or predictors. It's simple yet powerful technique which is used for prediction tasks. So to understand this better, let's take an example. Imagine you are a real estate agent who is trying to predict the selling price of a house based on its size, number of rooms and locations. So here this linear regression would help you establish the relations between these factors and the house price. And the goal is to create a linear equation that best fits the observed data points, that is the prices of houses sold in the past. And there can be an equation like y is equals to b0 plus b1 into x1 plus b2 into x2 and bn into xn. So here this y will represent the dependent variable, that is the house price, and this x1, x2 and xn, they will be the independent variables which may be house size, number of rooms, locations, and these variables, this b0, b1, b2, they will be coefficients that needs to be learned from the training data. So this linear equation is used to make predictions of these new houses based on their independent variable. For example, you can estimate the selling price of a new house by plugging in its size, number of rooms and locations into the equation. Now why it is called linear? It is called linear because the relations between the variables is represented by a straight line, that is a linear function. And this line is adjusted to fit the observed data as closely as possible. So in practice, a slight deviation from the linearity is allowed, hence the name is called linear regression. So to summarize this, we can say that linear regression is a statistical method which is used to model the relations between a dependent variable and one or more independent variables. It's a powerful tool for prediction tasks, and it works by creating a linear equation that best fits the available data points. Now next comes the logistic regression. Now this logistic regression is a statistical method used for classification tasks similar to linear regression, but it models the relations between the independent variable and a binary, that is two class, or multinomial, that may be multi-class dependent variable. And the main difference is that it models the probability of class rather than its continuous value. So to understand this better, take an example. Imagine you are a talent scout who is trying to predict whether a new athlete will be a professional basketball player based on their height, weight, and performance metrics. So here this logistic regression would help you establish a relations between these factors and the likelihood of becoming a professional basketball player. And the goal is to create a logistic function that best fits these observed data points, that is the class probabilities of athletes in the past. So here this logistic function will output a value between 0 and 1, which can be interpreted as the probability of belonging to that specific class. So here the logistic function is used to make the predictions for the new athletes based on their independent variables. For example, you can estimate the probability of new athlete becoming a professional basketball player by plugging in their height or by their weight and by other performance matrices. Why it is called logistic? Because it uses the logistic function, which logisticizes the continuous range of values, that is minus infinity to plus infinity, to a probability range of 0 or to 1. So to summarize this, we can say that this logistic regression is a statistical method which is used for classification tasks, and it models the relations between independent variables and a binary or the multinomial dependent variables. And it works by estimating the probability of class. And it's a powerful tool for tasks such as spam detection, medical diagnosis, and fraud detection. Now next comes the sport vector machines. So these sport vector machines are a powerful machine learning techniques which are used for classification and regression tasks, and they are based on geometric interpretation of data, which makes them particularly effective for high dimensional data. So to understand this better, imagine you are a detective who is trying to classify a new suspect as either guilty or innocent based on the age, height, and criminal history. So here this SVM will help you find the best possible decision makers, that is a line or hyperplane that separates the two classes in the feature space. And the goal here is to find a boundary that maximizes the margin, which is the distance between the boundary and the closest data points, which are called sport vectors. And the larger this margin will be, the better the generalization of classifier. Now here the SVMs work by transforming the original data into higher dimensional space, where a linear boundary can separate the classes. So if the distance is not linearly separable, then it uses a technique called kernel trick to map the data into a high dimensional space where a linear boundary can be found. And there are two types of SVMs which are most common. First is the linear SVM, which works by finding a linear decision boundary. And this is efficient and works well for linearly separable data. And second is a non-linear SVM, which uses a kernel function to transform the data into a high dimensional space where a linear decision boundary can be found. And the common kernel functions include the radial basis function and polynomial kernel. So once that decision boundary is found, it's used to classify new data points. For example, you can determine the guilt or innocence of a new suspect by comparing their height, age, and criminal history to that decision boundary which is learned from the training data. So to summarize this, we can say that the sport vector machines are a powerful machine learning technique used for classification and regression tasks. And they work by finding the best possible decision boundary, that is the hyperplane, which separates the classes, and they achieve this by maximizing the margin between the boundary and the closest data points, which are called support vectors. And SVM is particularly effective for high dimensional data. Now next comes the K nearest neighbor. Now this K nearest neighbor is a simple and effective machine learning technique used for classification and regression tasks. And it works by finding the K closest data points, that is the neighbors to a given point, and make a prediction based on their labels or values. So imagine you are a librarian who is tasked to categorize a new book into one of the existing sections in a library based on its title, author and subject. So here this KNN would help you find the K most similar books or the neighbors in the libraries and use their categories to determine the new book section. So here the KNN will work by calculating the distances between the new data points and the existing data points, that is the books in the library. And the distance can be calculated using the matrices like Euclidean distance, Manhattan distance or Minkowski distance. So once that distance is calculated, the K nearest neighbors are selected and their class labels, that is the categories in the library class, they are used to make a prediction. So for the classification task, the most common approach is to assign the new data points the majority class of its neighbor. For example, if K is 3 and the new book's 3 nearest neighbors are in the fiction section, so the new book is likely to belong to the fiction section as well. So in the case of regression task, the value of new data point, example a book's price, can be estimated by taking an average of K nearest neighbors value. And here the value of K is an essential hyperparameter that needs to be chosen carefully. Because if the small K value will make the classifier more sensitive to noise and local patterns. But if you take large K value, it will make it smoother and more robust to noise. So to summarize this, we can say that this K nearest neighbor is a simple and effective machine learning technique used for classification and regression tasks. And it works by finding the K closest data points to a given point and making a prediction based on their labels. And it's particularly useful when the data is non-linearly separable and when the relations between the features are complex. Now next comes the gradient boosting. Well, that is a popular machine learning technique that combines multiple weak models, that is the base learners, to create a strong predictive model. And it works iteratively by training simple models on these residual errors of this previous model, which helps to correct their mistake and improve the overall performance. So imagine you are a basketball coach who is trying to improve the performance of your team. So instead of focusing on one player's weakness, you decide to create a team which is composed of multiple players with a different strength. And you arrange them in a specific order, and each player learns from the mistake of previous one. So in the context of machine learning, the weak models are simple models such as decision tree, linear models or neural networks. And the goal here is to train a sequence of these models in a way that the errors gradually cancel each other, resulting in a powerful ensemble. So this gradient boosting works by training as a sequence of weak models, typically decision trees. So at each iteration, a new tree is trained on a residual error of the previous tree. And here the new tree will try to correct the mistake of previous tree by focusing on the areas where the previous model performed poorly. And the final prediction is calculated as the weighted sum of the predictions of all the trees in the ensemble. And these weights are learned during the training process, and they determine the contribution of each tree to the final prediction. And they have several advantages. First advantage is robustness. For you are multiplying various weak models, so the gradient boosting can handle complex and non-linear relations in the data. Second is the interpretability. So this gradient boosting can provide feature importance ranking, which allows you to understand which feature is most important for the model's prediction. Also, it is adaptable, for it can be used with various types of base learners, making it a versatile technique. So the most common gradient boosting techniques are gradient boosting machines, XGBoost, light GBM or light gradient boosting machines. And these algorithms differ in their optimization technique, which is used to train the models, how they handle the missing values, how their parallelization strategies are used. So to summarize this, we can say that this gradient boosting is a powerful machine learning technique which combines multiple weak models to create a strong predictive model. And it works by iteratively training simple models on the residual errors of the previous model, which helps to create or also to correct their mistakes and improve the overall performance. So this gradient boosting is robust, interpretable and adaptable, making it a powerful choice for a wide range of applications. Now next comes the random forest. Now this random forest is a machine learning technique that builds an ensemble of decision trees to create a powerful predictive model. So it works by training multiple decision trees on different subsets of data and then combine their predictions to make a final decision. So imagine you are a detective who is trying to solve a crime by analyzing a series of clues. So instead of relying on a single detective with a limited perspective, you assemble a team of detectives, each with their own unique set of skills and expertise. Now this team will work together to solve the crime by combining their individual findings and insights. So in the context of machine learning, these decision trees are simple models that recursively partition the data into subsets based on the values of input feature, and each decision tree is trained on a random subset of data and a random subset of features, which helps to reduce the overfitting and improve the model's performance. So this random forest techniques works by growing a large number of decision trees, typically 100 to 1000. And at each split in the decision tree, this algorithm will randomly select a subset of the features to consider for splitting instead of using all available features. And this randomness ensures that each tree in the forest is different and has a unique perspective on the data. So whenever a new observation or the data point needs to be classified, each tree in the forest will predict its class of value, and the final prediction is made by aggregating the individual tree predictions. And the most common ways of aggregating the tree prediction is either by the majority voting. For classification problem, so the class with the most votes will be selected as final prediction, or averaging. So for the regression problems, the average of the prediction is used as final prediction. Now this random forest too has the various advantages like robustness, then interpretability and the generalization. So to summarize this, we can say that this random forest is a machine learning technique that builds an ensemble of decision trees to create a powerful predictive model. And it works by training multiple decision trees on different subset of data and finally combine their predictions to make a final decision. And they're robust, interpretable and versatile, which makes them a powerful choice for the wide range of applications. Then comes the dimensionality reduction technique. So this dimensionality reduction technique is used to simplify this complex data by reducing the number of features while retaining important information. So it's like a downsizing this large apartment complex into the smaller ones while still preserving this essential amenities and living spaces. So imagine you live in a big apartment complex with dozens of amenities like a swimming pool, gym, clubhouse, tennis house and more. So this complex has a high dimensionality with numerous features which will represent the different amenities. So to simplify this complex, you decide to build a smaller complex with fewer but essential amenities. So the new complex might have a swimming pool, a gym and a small clubhouse. And this process of selecting this most important features and discarding the less important ones, it's called dimensionality reduction. So in the context of machine learning, dimensionality reduction techniques are used to transform high dimensional data into low dimensional space while preserving the important patterns and relations in the data set. And this can improve the efficiency and effectiveness of machine learning algorithms, reduce overfitting and provide better interpretability of the results. Basically, there are two main types of dimensionality reduction techniques. First is the linear dimensionality reduction. So these techniques will use linear combination of original features to project the data into lower dimensional space. Example, you all know, principal component analysis. That's the example of linear dimensionality reduction. Then comes non-linear dimensionality reduction. So this non-linear dimensionality reduction techniques will use non-linear transformation to map the data into a lower dimensional space. And the examples can be t-distributed stochastic neighbor embedding and uniform manifold approximation and projection. So this linear dimensionality reduction techniques like PCA, they work by finding principal components, that is the direction of maximum variance in the data, and then project this data into a lower dimensional space along with these components. So this process will preserve the most important information in data while discard the less important details. And the non-linear dimensionality reduction techniques are used when the data has non-linear structure, right? So these techniques will aim to preserve the local structure of data while reducing its dimensionality. And they also will work by creating a lower dimensional representation that preserves the pairwise distance between the data points. So to summarize this, we can say that dimensionality reduction techniques will simplify this complex data by reducing the number of input features while retaining the important information. So it's a powerful technique which is used to improve the efficiency and effectiveness of machine learning algorithms and provide better interpretability of results. So this linear dimensionality reduction techniques, they will use linear combination of features to project the data into lower dimensional space, while non-linear techniques will use non-linear transformations to map the data into a lower dimensional space. Then comes decision tree. So this decision tree algorithm is a powerful tool which is used in machine learning for making predictions and classifications. So it's like a predictive flow chart that helps identify patterns in data to make accurate forecasts. So imagine you want to predict whether it will rain tomorrow. So here this decision tree algorithm would start with the question, what's the current weather like? So based on your answer, sunny or rainy, the algorithm would lead you to a series of questions such as what's the humidity level, what's the temperature. So this decision tree algorithm is designed to make predictions by analyzing various factors and their relations with the outcome. And each decision you make along the way, it helps narrow down the possible outcomes until the algorithm reaches the final prediction. So in the context of machine learning, this decision tree algorithms are used to analyze these large data sets and identify the patterns which can be used to predict outcomes for the new unseen data. And these algorithms can be trained on historical data to make accurate predictions, such as predicting whether a customer is likely to buy a product or identify potential health risk based on medical data. So in the layman term, a decision tree algorithm is a predictive flow chart that helps identify patterns in data to make accurate forecast. It's a powerful tool used in machine learning to analyze large data sets and make predictions for new data based on historical trends and patterns. Now next comes the clustering techniques. So this clustering is a powerful technique in data analysis that helps group similar objects or data points together. So it's like sorting fruits in a basket based on their color, shape or size. And the goal of clustering is to identify patterns in data and organize them into meaningful groups called clusters. So imagine you have a bunch of different color beads, red, blue, green and yellow. So clustering technique would help you grow the beads into separate baskets based on their color. For example, you might put all the red beads in one basket, all the blue beads in another, and so on. So in the context of data analysis, these clustering techniques are used to organize this large complex data set into groups that share similar characteristics. And there are various clustering techniques such as k-means, hierarchical clustering and density-based clustering. And these techniques analyze various attributes of data points such as numerical vectors or categorical variables and use these attributes to determine the similarity between the data points. And this k-means clustering, for example, starts with clusters and iteratively moves this data point between the clusters to minimize the sum of distances between the data points and their cluster centers. So hierarchical clustering, on the other hand, will build a data tree-like structure. So where each data point is initializing a cluster and then the clusters are iteratively merged based on their similarity. So to summarize this, we can say these clustering techniques are a powerful tool which are used in data analysis to group similar objects or data points together into a meaningful cluster. It's like sorting fruits in a basket based on their color, shape or size. But instead of fruits, it's applied to large and complex data sets to identify patterns and organize information. Thank you.